So my goal today now that we've watched that kind of crash course YouTube video, our goal now is to discuss the current model of the atom, the quantum model. And let's begin with what the one YouTube video presenter finished with. We don't believe this is right. I think physicists especially have gotten a little bit of humility in terms of the number of times that they're like, okay, we got this, everybody. Good job. Physics is all figured out. Pat yourself on the back. And then realize, oh, never mind. We were maybe not all the way right. Science, by its very nature, should always be continually being more and more discovered. I just want to point that out because I always find it frustrating when I hear people say, like, science is hard and confirmed. We know 100% what is true. It's like we actually know that we don't know that sometimes, right? Modern physicists are working on string theory. Anyone ever heard that phrase before? It's basically the idea of, well, what if we can go beyond electrons and protons, beyond when we eventually talk about quarks? What if we go even smaller than that? And physicists are trying to figure out, well, maybe the universe is made of these vibrating strings. Some physicists are working on ideas like dark matter and black holes and radiation, and we don't have all the answers, which I think is cool. It's one of the things that I like about physics, is that we're fairly certain that we know certain properties, but at other times we know that there's actually a lot of stuff that we don't know, and that makes it exciting, I think. Okay, back to quantum model. So I want to go back to the year 1911, 1913, somewhere around then. Bohr suggests a new model for an atom. He has this idea that electrons are lined up in rings. I'll just draw it one more time. You must have seen this before in a chemistry class. You put a nucleus here, and you start to draw these rings. And one of the ways we can draw them is like this. You're probably familiar with the idea of like 2 electrons in the first level. Well, actually, 2 would be in the first level. Then 8 in the second level. Maybe you've seen electron dot diagrams where sodium has 1 valence electron, chlorine has 7 valence electrons. And that's what Bohr's model allowed us to visualize and conceptualize. The problem is those electrons. The question is, well, are they really in just a circle? Is that truly their location? And we kind of now understand that that's not really where they are. They are in levels. But yeah, I don't want to think of those levels in like 3-dimensional regions of space. You need to think about more about waves. Because I want to bring back in a different scientist here. His name was de Broglie, and we talked about him in our last unit here. I'm just going to highlight his name. De Broglie had shown in 1923? Yeah, 1923, de Broglie had made a prediction that if waves can have properties of matter, he suggested, what if matter can have property of waves? And this actually kind of helped tie this together as to why there might need to be these very, very specific orbitals. I think this picture right here helps illustrate this. If electrons are behaving as waves, and granted, when I think of a wave, I can't picture an electron wave. I don't have that ability. But I can picture like a physical mechanical wave, like a wire that's bouncing up and down, right? So don't think of the electrons as actually traveling along a path like this, because that's not what we're suggesting they do. But we're just suggesting that if they're behaving like a wave, this is the best visual way you can picture a wave. Here's a wave that's going up and down once, up and down twice, up and down 3 times, up and down 4 times, up and down 5 times. And so based on this picture right here, I believe I fit 5 wavelengths of an electron going up and down in this particular location. But right here, if I had a slightly smaller circle, I guess, again, keep in mind, it's not really a circle, but this is a good way of representing it. Here the wave went up and down once, up and down twice, up and down 3 times, and then it didn't quite fit. The number of wavelengths required to fit at this particular, let's call it a radii, at this particular radii right here, the waves don't fit enough. And that was basically how de Broglie's model kind of came in together with Bohr's. So he was able to suggest, well, what I could do is I could say that right here I could have 1, 2, 3 waves. I didn't draw very well, but that could be, say, 3 waves right here. And then over here I could have 1, 2, 3, 4 waves. But it's not possible to ever find an electron in this location here, because it would be halfway between 3 wavelengths and 4 wavelengths, and that's really not a place that you'd ever find an electron. And again, this is not a great model because I'm trying to think of an electron as though it's going up and down and up and down, but not all waves actually work in that sort of capacity. Mechanical ones do, right? Like physical moving of mediums do. But that's where that's what makes quantum physics so hard to imagine, is because you're trying to imagine something that we have no reference to in everyday life examples. But the basic concept is that it did kind of fit now, because for the electron to, let's put it in quotes here, orbit the nucleus, because orbit's really the wrong word, but for an electron to orbit the nucleus, the wavelengths must be able to perfectly fit, which then allows for this concept of these like concentric rings. Does that make sense so far? So like this first ring right here, let's call it energy level 1, it might have 1 wavelength around it. This one right here might be 2 wavelengths. This one right here might be 3 wavelengths, and therefore you're never going to find an electron halfway in between. But we do know that electrons have the ability to bounce between these different wavelength levels, because you could have 2 wavelengths or 3 wavelengths or 4 wavelengths. You can't have 2.5 or 1.75. And that's why we call it a quantum model. Because what does quantum really mean? Quantum means kind of the opposite of continuous. If I were to give you the word continuous, continuous means you can have any value you want. For example, if I were to ask you how far it is from here to the door, you might say that it's 12.973 feet or something like that, right? And if I wanted to, I could always become more and more precise and add more digits. That's a continuous value. You can use literally as many digits as you'd like to. But there's some things that are discrete. As an example, shoe size. You either buy size 8 shoes or size 8.5 shoes. But you really can't buy, well, unless you have a really good shoe distributor, you can't buy size 8.234 shoes. You get what I'm saying? So quantum really refers to discrete. The fact that you have to have like a fundamental amount of something. You can either have 1 wavelength or 2 or 3, but you can't be found in between. Right? It's breaking the idea of a limit. Rather than being able to get closer and closer and closer to a value, you're telling me, no, the smallest possible number in the world is this. My daughter's in grade 1, and it's fascinating hearing her talk math, because I mean, being a teacher, I love hearing her math, right? And so she'll ask, Dad, what's the biggest number in the world, right? And then she'll say, like, infinity. And then she'll ask me questions that are silly, like, Dad, what's infinity plus 1, right? And like, she's already grappling in her mind with the idea of like, well, what is the biggest number out there, right? But really, this is just taking the opposite extreme. If I were to ask everybody, what's the smallest number there is? Like, not like most negative, but what is the most small number that exists? What's the closest number to 0 that you can possibly have? How can you even possibly answer that question, right? If I were to say that it's 1/1000th, someone might say, well, what if it is 1/1,000,000th? And someone might say, well, what if it's 1/1,000,000,000th? In theory, what you've learned in calculus, for those of you who've done that, is that you can always make it smaller. That's the opposite of what these guys are saying. They are saying that at a fundamental level, you cannot get smaller than that. And that explains why this ring right here, which has the ability to fit 2 electrons in it, is the smallest energy wave possible. So, very weird way of thinking about it. So because they're suggesting that perhaps the electron behaves as a standing wave, and it's not really a particle, the accelerated charged particle of Maxwell's theory no longer applies. Right? If we were under the impression that the electron is behaving as a particle, then yeah, if it's traveling around in circles, then it should, in theory, lose electromagnetic radiation, spiral into the center, and all matter would, I guess, like collapse on itself. But wait, if it's not actually an electron as matter, what if it's a wave? Then if it's a standing wave, then it's no longer an accelerated charged particle. And now we're back to that whole weirdness of, well, which one is it? Is it an electron or is it a wave? Is it matter or is it a particle? And if the answer is both, depending on what it needs to be, boy, that is a strange concept. It's like, how can the electron just choose to decide to be a wave when it's convenient and to choose to not be a wave when it's inconvenient? Like, isn't that more or less what we're trying to say here? Is that it basically it decides what it wants to be based on the convenience? As soon as you look at it, all of a sudden it becomes a particle. But if you're not trying to detect it, now it's a wave. So here's what we do then instead of trying to nail down that exact position of an electron. We call it a cloud. That's the most current model of the atom. And the cloud basically suggests, okay, we're going to try to pinpoint where this electron is. But it's not really an electron, it's a wave, which means it's kind of everywhere at the same time. And so we draw this cloud, which is, sometimes it's more of like an artistic model. Because again, we don't really have the ability to hop on a magic school bus, zoom down to size, and find the electron. Right? Like, that's what makes this so impossible to describe. So this electron cloud is more about probability. And it suggests in some sort of artistic rendering where we believe the electron is most likely to be. If we were to look for it, it would stop being a wave and it would be a particle. Right? We say that again. If we were to look for it, it would stop being a wave and it would be a particle, like we've learned in the double slit experiment. And so if we were to try to observe it, it could be found here. But the next time you try to observe it, it could be found over here, and then over here, and then over here, because who knows where it's going to show up. In theory, through the principle of superposition, it's everywhere at once until you look for it. And so right here, this blue area right here is the most dense. It doesn't mean that there's more electrons there. It just means that there's more of a chance we think we're going to find the electron there once we look. It's so strange. That's what I love about it. Now, our current periodic table is actually configured in such a way. I don't know how much of this you guys ever get into in your chemistry classes, but there are different sorts of orbitals that maybe you've heard about. These things right here are considered to be electrons that are found in what's called the S block of orbitals. This section over here is the P block of orbitals. Your transition metals are known as the D block. And your lanthanide and actinides, the ones that are like, you know how it's supposed to be inset into the periodic table over here, these ones are known as the F block of orbitals. And if you get to a certain level of chemistry, probably you didn't cover this in grade 11 or 12. Maybe you did, depends on your teacher. But we actually believe that this is where electrons are found. And so those drawings that you learned about in chemistry where you draw sodium like this, that's really kind of incorrect. What we believe is that sodium actually has a mixture of many of different locations as to where those electrons are. We don't actually think that sodium has 2 electrons here, and then 8 electrons here. And then what's sodium? Sodium's 11, right? So there should be 1 more, I think. Ooh, what am I doing here? Sorry. And then 1 electron in the outermost region there. What we believe, though, is that this electron right here that we've drawn in the outermost region, we believe it's found in a region of space somewhere right here. And then some of these electrons here, we believe those electrons are actually found in these p orbitals. And they have a weird geometry, apparently, to them, where there's like some could be on this side of the atom and some could be on this side of the atom. And we have to try to draw them now in 3 dimensions. The problem with this Bohr model is that it's really trying to be drawing something in 2 dimensions, but we have a 3-dimensional world. Do not worry about this. We don't actually ever assess on this sort of information here. I didn't learn about this until I took Phys Chem 1. I think it was Chemistry 2700, and that was in my second year of university, the first time I learned about this. So, like, I'm going a little bit beyond the physics curriculum, but the reason why I feel compelled to do that is I need to explain to you what physicists, at least I'm trying to explain in a small degree, what physicists believe electrons actually are found in. And so we draw these like these bubbles or clouds that represent possible locations for electrons. Which is kind of weird because there could be electrons somewhere in this bubble, somewhere in that bubble, somewhere in that bubble, somewhere in that one. And as soon as you get to the biggies, like the F series, those are your lanthanides and actinides, they could be kind of anywhere. So, because this is a really confusing topic and is also, I'm already well past the bounds of physics 30, I need you guys to basically know this. If you can understand the idea that these concentric circles here are really not a good visual picture, if you can even understand that, if you can think of it as a wave that's going around like this, not actually physically an electron traveling on this path, but the electron is behaving as a wave, which again, I don't feel bad saying this, I cannot picture what that is like in my mind. My brain doesn't interpret what a wave is unless I think of a physical wave. But if you can kind of understand that concept and just know that this is our most current picture, that this is a probable likelihood of where we find it, that's all you need to know. Okay. If I could, though, I want to show you one more YouTube video. This is, honestly, this is beyond some of what I remember, because I haven't done my chemistry in university in a while. But this is his next lesson in the series, the one guy that I showed you his video. He's going to talk a bit about those orbitals, and so please don't stress over memorizing any of this. But I think we should talk about it while we're there. So this is that crash course chemistry guy again. Only now he's going to talk about orbitals.
I'm thinking about atoms is looking like this. There's a ball and there's a stick, and another ball and another stick. Just a bunch of balls stuck together by these little wooden prongs. Simple.
You guys ever do those in your chemistry classes? Right. If I were to ask you a question, whose model of the atom does that best represent? Who would you suggest? I'd say Dalton is probably the best one, because this really imagines an atom more or less as a ball. Right? That's probably best described as Dalton, because there's really no evidence here of electrons internally. There's no really evidence here of a nucleus. So this is using basically John Dalton's model of like a ball. And we use these little sticks here to represent electrons. What we're going to talk about in this video here is that that is really not at all how we believe the electrons work. The electrons are impossible to find, and they certainly don't come together and make this like little wooden bridge that somehow combines things. So anyways, let's keep watching. Ooh, I think my pad lost connectivity.
As you have probably come to expect, it is entirely incorrect. Nuclei really can be understood as blue balls, and that's more or less correct. So when you get to some of the bigger, less stable ones, they start looking more oblong and weird, like a rugby ball. Atoms are basically ball-like as well, with electrons in a spherical cloud around the nucleus. But molecules, as we discussed last time, do not look like balls on sticks. Bonds don't form a neat little line. They form from overlapping electron clouds, or shells, flowing around the nuclei of bonded atoms. We really get down there and understand what they look like. The lumpy, clumpy globs of probable electron locations. And these lumpy clumps of probable electron locations.
I want to see that phrase again.
Understand what they look like. The lumpy, clumpy globs of probable electron locations.
That's probably the best way of describing it. They're probable electron locations. Because again, as soon as you would try to find the electron, now it exists in one spot, but until you look for it, we believe it exists everywhere at once. Ah, I love this stuff. It's so cool. I can't wait to show you the video we're going to watch next week on Wednesday, because it walks through all of this concept, including the idea of how there's theories about how there are parallel universes out there, and how there could possibly be a multiverse. That's not actually just like science fiction. Physicists actually believe this. So, anyways.
And these lumpy, clumpy, probable electron locations do not behave the way you might initially expect them to behave. No, that would be far too simple. They behave based on quantum mechanical three-dimensional wave functions, probabilistic distributions of electrons in space. And yeah, by the end of this episode, you're going to understand what I just said, and it's going to be awesome.
I'm not even sure that I understand what you just said, because I mean, it's hard even to put quantum physics into words.
Let's start with water, because all the interesting things on our planet start with water. It's also universally common, not just on our planet, but in our galaxy and our universe. Case in point, in 2011, astronomers discovered a cloud of water ice surrounding a black hole that contains 140 trillion times more water than we have here on Earth. And while we don't have any confirmed worlds covered in water outside of our solar system, we do have some right here in our solar system. Europa contains so much water, probably salt water, that its entire surface is just ice. What did any of that have to do with atomic orbitals? Nothing. I just felt like maybe I scared you with all that quantum mechanics talk before the intro, and I wanted to chill you out for a second. Okay, so water. We did its Lewis structure last week, remember? Each hydrogen bonding with the oxygen atom, and voila. But that drawing is linear, just a straight line through all the nuclei. And we know, just instinctually at this point, that water is a bent molecule. But why? Why is water crooked? Unbonded atoms within a molecule generally like to be as far away from each other as possible, especially if they have the same partial charge as the two hydrogens do with their partial positives. But something is keeping those hydrogens closer together than they would like to be. So why on earth are they not stretched out as far away from each other as possible? I ask this because if they were, the water molecule wouldn't be polar, and if water was suddenly non-polar, we would all instantly die, as would all life on Earth. And suddenly we realize that this seemingly normal thing that we all knew about the world is really weird. And weird stuff is my favorite stuff because it means interesting questions. Interesting questions I want to know the answers. It's an even more compelling question than what the heck is a quantum mechanical three-dimensional wave function? Well, of course, the answer to this question has a great deal to do with quantum mechanical three-dimensional wave functions, so let's start there. Oh, look! I've got a telephone cord. This is what old people used to use to get their voices into wires so they could be transmitted across the world before cell phones. But today, it's pretty much only useful for demonstrating electron fields. Electrons are both particles and waves, which is not an easy thing to imagine. Very basically, you can think of them as an excitation of the electron field, which exists everywhere. When energy is dumped into the electron field, electrons exist inside a wave function. What's a wave function? It's a mathematical function that describes the probability that an electron is in a certain place at any given moment. So if this telephone cord is an electron field, I dump some energy into it and we create what's called a standing wave. The wave function is a mathematical function that describes it.
sure he's going to talk about it here, but this is basically what I was just saying here. This idea of the standing wave of the electron moving around like this. Again, you're going to see him have this little electron move like that, but I think that's just the best way of us trying to visualize something that really it's hard to visualize. What does a standing wave look like for an electron?
This excitation from the electron field around the nucleus in a standing wave. The simplest of these wave functions is the s orbital, which can contain 2 electrons and is a spherical pattern of standing waves around the nucleus. This standing wave can have different numbers of nodes, allowing patterns to repeat themselves when there are more electrons around the nucleus. Every orbital can contain, and indeed is at its lowest energy when it contains 2 electrons. Hydrogen has 1 electron in its s orbital. Helium, an ultra-stable, very low-energy noble gas, has 2. It's happy because it has its shell filled. But of course, there are other sorts of orbitals as well. After we fill the first and second s orbital, we move on to fill in the p orbital, or rather, I should say p orbitals, because we're talking about 3-dimensional space.
Okay, quick little chemistry lesson here. I'm going to turn the lights on to talk about the periodic table. This is actually why, chemistry-wise, the periodic table has been built the way it is. That's my laser pointer. For those of you guys who are familiar with the periodic table over here, one of the reasons why we build it the way it is that there's this big gap right here in the middle, right? And some kids ask, well, why don't you just go lithium, beryllium? Why don't we put boron right next to it? And one of the reasons why it's been separated is, I mean, yes, it has to do with the fact that all of these things are in the same group. They have similar properties. You guys learn that in chemistry, right? Like all of these guys right here in the gray column, they're all halogens. These are all noble gases. But another big reason for the split is that if you look at this one right here, there's actually 3 known p orbital orientations. There's one here and here, here and here, here and here. And so you can actually see how there's 1, 2, 3, 4, 5, 6. Each electron, do you guys ever talk in chemistry 20 about VSPR, VSPR, valence shell electron pair repulsion theory? We recognized actually that electrons always go in pairs. And so in these 2 bubbles right here, we believe there's 2 electrons. And in these 2 bubbles right here, somewhere in there, there's 2 electrons. And in these 2, there's 2 electrons right here for a grand total of 6. Looking at this part of the periodic table, that's why there's 6 across right here. That makes sense? And in the previous one that he had on the slide here, where it was just a sphere, somewhere in that sphere are 2 electrons, and that kind of accounts for why these things always kind of come in 2s right here to some degree. If you ever get to the D and F orbitals, which I can't even remember from my university career, but like those would be these ones right here, and that's why you'd expect to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But 10 divided by 2 means there should be 5 different orientations of shapes. And maybe in some of these pictures, you'll see how there's 5 different shapes. This right here kind of explains where the periodic table came from. Again, I'm going well beyond this course, but I feel compelled to just kind of try to wrap it all up so that you get how the chemistry and physics meet.
Is here, so there can be one on the x-axis, one on the y-axis, and one on the z-axis. Even though you contain 2 electrons for a total of 8, with 2 in the s orbital and 6 in the 3p orbitals. And yes, those 8 electrons are the reason for the whole octet rule thing. Remember now, the periodic table is a map of the orbitals as they fill. Elements in the s block are filling their s orbitals, elements in the p block are filling their p's, same with the d's and the s. So s orbitals very simple, spherical, p orbitals a little bit weirder, d and f orbitals so crazy. Some of the f orbitals in particular have just ridiculously cool geometries. Lots of fancy math is involved.
There's 7 there. Times by 2. 14 should be how many we have on the bottom row. Does that make sense?
In the second shell, we have an s orbital and 3 p orbitals. The p orbitals, if they were all by themselves, look like this. But when you actually stick them around an atom, the s and p orbitals start to interact with each other, doing your best not to overlap and changing each other. The s and the p orbitals can merge into hybrid sp orbitals. Instead of being 2 different kinds of orbitals, they become 4 identical orbitals trying their best not to overlap. This is called orbital hybridization. When the s orbital hybridizes with all 3 p orbitals, it's called sp3 hybridization, and it forms a tetrahedral shape. And this is that tetrahedral shape. It's the easiest way for all the orbitals to form something like a sphere around the atom, but not interact too much. I didn't do anything fancy to make it.
I'm actually going to stop the video there because it gets more and more complicated. I just thought I'd kind of go up to this point because if any of you have taken Chem 20, did you ever talk about the different shapes that atoms make, where there's tetrahedral, linear, trigonal planar, trigonal pyramidal? At least for those of you who took Chem 20, that's more or less what he's showing right here, is that these orbitals that you're seeing in those 4 different directions, those represent the electron clouds as to where electrons could be found. And that's what makes actually chemical bonds, is the overlapping of electron clouds. It's not actually two electrons that are like somehow gluing themselves together. It just happens to be that when electron probable locations come near each other, that's what makes a bond. So, okay, that's my lesson. Kind of ending that with like a weird sort of section. Can I just recover go over what you need to know one last time? Because I'm definitely going beyond. Let me just go back here. Where's my notes? So here's what you guys need to know. You need to know your timeline. Okay, you need to know what scientists accomplished what and what their achievements were. You should know about the main ones for this unit will be Dalton, his model in 1803 of indivisible particles. 100 years or so later, J.J. Thomson discovers cathode rays, thinks that they're waves at first, then realizes no, they're particles. They are 1,000 times smaller than the previously known smallest particle, which was hydrogen. He then gets this idea of subatomic particles for the first time, which breaks the rule that Dalton had, because Dalton thought you couldn't cut things in half. And now Thomson says, maybe there's stuff inside there, right? He has the plum pudding model. After that comes Rutherford. Rutherford discovers the nucleus and makes a change. Now the electrons are no longer kind of internal, they're more external. The question is, what are those electrons doing? They're not actually orbiting. He knows that's wrong. Two reasons why. One, if they were orbiting, they'd be giving off electromagnetic radiation. We'd all be dying of radiation poisoning just by having matter nearby. And two, that would mean that matter itself is collapsing on itself, which it clearly isn't. The other reason why is that whole spectrum tube, where they were able to see these distinct bands of light. They couldn't figure out, why do you only see these just special distinct colors through that diffraction grating like I showed you in the experiment the other day. Putting it together, Bohr realizes that maybe these things are in what he called orbitals. We still use that word today, even though we recognize that they're not really orbiting. But he suggested that electrons either exist in this ring or this ring or this ring, never in between, and as they hop back and forth, they either need to absorb or release energy. Modern theory looks more like this, where once we recognize that electrons really aren't particles, they're wave particles at the same time, you hear all this fancy gibberish called like probabilistic wave functions, which basically is this illustration here where you're trying to say, well, where is the electron? I don't know, somewhere in there. We don't actually know until we look for it. If you look for it, it might be right here. If I look for it, it might be right here. And that's what makes physics so weird, is that you'd like to think that you could reproduce the exact same result every single time, and yet you don't. If you do the exact same thing and run the same experiment 10 times, you might get like 6 different results. And so that's how they figure out probabilities. There's some things that happen more often. When they looked for the electrons, more than likely they found it here, but sometimes they found it in weird and unusual and you wouldn't expect to find it sort of places. So, and that's what you guys need to know. Maybe finishing it off here, this picture that I had right here, probably the best way of describing it, at least it's the best way I can make sense of it in my mind, is that if an electron really is a wave, this now explains why the energy levels exist, because if the wavelengths fit, then that's a possible location. If the wavelengths don't fit, then that's not a possible location. And that's why quantum physics is still being worked on to this day. So, okay. Does anybody have any questions on that? I'm sure you do, but I'm not sure you even know how to articulate them or even if I could answer them. So. Okay, let's pause here. I'm going to give you guys your unit tests back in just a few minutes here. Let me talk to you guys about where the rest of the unit goes. We're actually halfway down this unit, and there's no math equations. When you guys come back, we're going to talk about radioactive decay. I've made a YouTube video for it, so you could actually watch that if you'd like to ahead of time. This will be the last one I make a YouTube video for. Radioactive decay was a natural extension of quantum subatomic particles, trying to discover how there's certain isotopes of matter that are no longer stable, and they give off radiation. So we're going to spend a day talking about that. Then we're going to spend a day talking about the 1930s and the 1940s. And there was a really big moment in not only scientific history, but in world history. In the 1940s, in the 1930s, Adolf Hitler rose to power. This is where the social studies kind of overlap comes in. And the Germans, the Nazis, they were working on an atomic bomb. What's his name again? Einstein, Albert Einstein. He actually famously wrote a letter to FDR, Franklin Delano Roosevelt, basically saying, U.S., get off your butts and start making a nuclear bomb, because if you don't, Germany will. And if Germany beats you to the atomic weapon, who knows what sort of world we'll live in. And that's actually a really kind of crazy story as to how the Manhattan Project started, where nuclear physicists like Enrico Fermi, Robert Oppenheimer, they started to work on one of the most intense and short-framed projects to make the first nuclear bomb, which you guys have probably heard about this in social studies class, was dropped in Japan in 1945. And although that sounds like social studies, because, I mean, obviously it is, and it had major world implications, the physics behind it is actually probably maybe the more important story of trying to figure out how to harness the energy found inside of these bonds that we're starting to discover at the subatomic level. And I don't know that I could overstate it enough. That's why I even put it on my timeline if you haven't read it here. Little Boy was dropped in Hiroshima in 45. In 42, Einstein writes to FDR basically saying, guys, you got to start working on this, because if the Germans beat you to it, who knows what's going to happen. We'd live in a radically different world, I'm sure. So, anyways, that's kind of where our next little bit goes. So we're going to talk about radioactive decay and how that allowed scientists to figure out nuclear bombs and fission and fusion. And then our final lesson will be on some of the weirdest stuff, antimatter and quarks. Antimatter basically is like, how do you even describe antimatter? It's like the opposite of matter. And how do I even describe it? I don't know. Quarks I can describe better. Quarks have to do with what is the subatomic particles. So if we think that the periodic table is made of these things over here, but they're really made of protons, neutrons, and electrons, quarks now gets into, well, what are the electrons made out of? What is that made out of? And what's that made out of? And yeah, this is kind of basically history-wise, this takes us up to more or less modern-day physics and what they're working on. So. Okay, sound good? Okay, let me stop my recording here first.